Good afternoon, and welcome to our talk on GPU-accelerated distributed ML and Apache Spark clusters. My name is Erik, and I'll be co-presenting with my colleague Jinfeng Li, who's seated right there. He'll be coming up at some point. As we're both from NVIDIA, before proceeding with the talk, I'd like to give a quick shout out to the two announcements from joint announcements from Databricks and NVIDIA from yesterday's keynote. First part being making the DBRX models and follow-ons from Databricks available as NVIDIA Inference Microservice, or NIMS for short, which is part of the NVAIE software product with enterprise support and API catalog. And then the second huge thing was a collaboration on bringing NVIDIA GPUs to accelerate Photon, the core vectorized query processing engine in the Databricks platform. Okay, so with that, I'm going to launch into the talk, and just to make clear, this talk has nothing to do with either of those announcements. Just wanted to get that out there. Oops. Okay. So roughly 4 years ago, GPUs were added as a schedulable resource in Apache Spark. And that, along with some other innovations, opened the door to what we see as the era of GPU-accelerated Spark, and we think is essential for allowing Spark to keep up with the ever-growing requirements of data processing. So at NVIDIA, we have a Spark team working on figuring out how to GPU accelerate Apache Spark. And to realize this potential, we have been developing the NVIDIA RAPIDS accelerator with two modules, respectively targeting accelerated batch data processing for Spark SQL or data frames. And most recently, the new kid on the block and the main topic of this talk is accelerating machine learning via Spark MLlit. Both of these modules are two separate Apache 2.0 licensed open source projects. And we'll refer to them, the SQL accelerator, as the RAPIDS accelerator for Apache Spark, and the ML part as the RAPIDS accelerator for Apache Spark ML. Those are kind of the official names, but sometimes we'll refer to them as Spark RAPIDS plugin for the SQL part and Spark RAPIDS ML after their GitHub project names. So the overall approach for both of these has been to build the accelerators on top of a foundational NVIDIA software library called RAPIDS. It comprises a suite of highly optimized C++ libraries for NVIDIA GPU, accelerated core computations needed in data processing and machine learning. And originally, they weren't developed for Spark at all. They were, in fact, developed to accelerate the Python data science ecosystem. But the Spark project came in and figured out how to leverage all that awesome work to help the Spark effort. So before diving into the ML part of this, which is the main topic of the talk, I'd like to quickly review the data processing module, the Spark RAPIDS plugin, in case that's new for some of you. So the Spark RAPIDS plugin, it's a plugin jar. You can download it from Maven. And if you put that jar in the class path of the driver and the executors, and you configure a setting called Spark plugins to point to the main plugin class, you accelerate Spark SQL, example on the right. And not only Spark SQL, but also the Spark Data Frame API is accelerated, and so is pretty much any other language binding like R or so forth that ultimately gets converted to so-called catalyst operators. It works with all Spark schedulers, distributions, CSP hosted Spark services, etc. And the best part is that no code change is required to get this acceleration. And with, of course, that the result of the query is the same, whether you accelerate it or not. That's crucial, obviously. Not all operations are accelerated. So for example, RDD operations and most user-defined functions. Even in these cases though, you don't have to remove them or change your code or anything or convert them to data frame. The plugin will simply just fall back seamlessly to running those on CPU. So yeah, even if it's not accelerated, no code change is required. So the RAPIDS accelerator for Apache Spark can significantly accelerate query processing and also reduce infrastructure costs. So as an example of this, here are the results of a recent CPU and GPU runs of something called the NVIDIA Decision Support Benchmark, which is a slight variation on the well-known TPC-DS benchmark, essentially just to get it to run in Spark SQL. There are a few changes here and there required to do that. In this case, both CPU and GPU clusters had 8 nodes, standalone, so baseline open source Spark, running on AWS EC2 instances, so standalone cluster on EC2 instances of the type shown. The G5s have A10 GPUs from NVIDIA. And as you can see, the GPU runs correspond to the green bars and the CPU to the blue bars. You can see that we get about a 5.5x speed up on this benchmark and at 80% lower cost, which is determined just from the cloud, the instance costs. This is a mature, the Spark Rapids plugin is a mature project. It's been underway for probably 4 years now. It is actually recently has been added to the NVAIE Enterprise class software product. So it comes with enterprise support. And there are going to be some links on the last slide if you want to learn more. It's been presented at past Data AI Summits. In fact, there was a talk on it yesterday by our colleagues, Jason and Nikolai. So that's all I'm going to say about the data processing acceleration part of this. So let's get back to the main topic. And at this point, I'm going to turn it over to Jinfeng to dive into the ML part. And then I'll come back a bit towards the end.
Thank you, Erik. So next I'm going to present in detail the ML accelerator. This project targets at PySpark. It only supports Python API and it does not support Spark Scalar API. This is an open source project with a 2-month release. And similar to the accelerator for SQL and data frame, the ML accelerator can run successfully on the major cloud environments, including Amazon EMR, Google Cloud, and Microsoft Azure. It can also be easily deployed on-premise on your own clusters. Underlying the implementation, it mainly leverages the NVIDIA RAPIDS software library, and I'm going to introduce it in details later. This slide shows a typical machine learning application code. The Spark users should be familiar with that. The application code starts from converting a raw data set into feature vectors, then pass these feature vectors to a machine learning algorithm, in this example K-means, to fit a model. So this code currently runs on, most people know that it runs on the CPU, with the accelerator for SQL data frame and the ML accelerator. The same application code can get GPU acceleration. Next, I'm going to introduce some key perspectives of the ML accelerator. The first one is the API, how to use it. The ML accelerator targets at fully compatible with existing PySpark APIs, which means that it requires no code changes. To use GPU acceleration, only needs to replace the import statement. The right-hand side shows the example of using K-means to cluster a data set This is a pure CPU code. You import the k-means from PySpark library, set the parameters of the algorithm, and next call fig function to train a model on your data set. And when training finished, you may dump the model to disk or use the model to make inference on the data frame. In order to use GPU acceleration, the application code only needs to change the import statement to Spark RAPIDS ML. And the computation-heavy APIs, including the Fig API and Transform API, can get the GPU acceleration automatically. This design has several benefits. First, you can get it working with existing the application codes, no code change, while can accelerate your machine learning section of your application code. And second, the developers do not need to learn new APIs. Next, I'm going to introduce some details about the implementation. Underlying, it mainly leverage the QML. The QML is a project targeted at the machine learning library scikit-learn, and it provides a list of algorithms. One nice feature of QML is that it has the implementation of multi-node over those majority of the algorithms. And to support GPU to GPU communication, it leverages the NCCL communication. The NCCL provides a set of collective operators. One example is Ordentlich, that you can calculate the mean or sum across the distributed data sets. Very easy to use and important for many machine learning workloads. And the requirement, QML and NCCL has a requirement, one process per GPU. So to satisfy that requirement on Spark, we need to make sure one task per GPU scheduling and launch all these tasks at the same time. And when PySpark users use an algorithm, either PCA or k-means, the difference is that it converts to the QML different multi-node GPU classes. The ML accelerator is just a thin layer to wrap the PySpark API to QML API. This slide shows a bit more detail about the implementation, the pseudo code. So the k-means algorithm, when the application code call fig function or Spark data frame, or as data set here, the ML accelerator will map Spark params to QML parameters. And the next, we'll use Spark API repartition to ensure the number of tasks match exactly the number of GPUs in a cluster. And the next, use map in pandas that takes a Python function in order to call QML. And last is the barrier RDD that will ensure to launch all tasks in the cluster at the same time. And when training finished, the model will be returned back to the CPU, and the CPU will take over the computation from here. The ML accelerator will handle the automation that will copy your CPU dataset to GPU, leverage GPU to compute, and get the GPU result back to CPU. Inside this train UDF Python function, the ML accelerator mainly converts the PySpark pandas data frames into array type that can accept by QML. In this case, the NumPy array. It also leverage PySpark barrier task context API to bootstrap an NCCL communicator. The NumPy array and communicator will be passed into QML to enable the GPU training. From these slides, I'm going to present the algorithm list currently supported in the ML accelerator, categorized into 3 groups. The largest group on the left, you should be very familiar with that. This is the algorithms common in Spark and QML, such as the k-means for unsupervised clustering and logistic regression for supervised classification. And the group next to it is the QML only algorithms that are not available in Spark yet. These include the exact K nearest neighbor search that can be used to apply approximate nearest neighbor search on feature vectors. And the next one, UMap, is for nonlinear dimension reduction. Project your high dimensional data into low dimension for visualization of some follow-up analysis. The DB scan, which is known as another density-based clustering algorithm. And the last one, IV flag approximate KNN, is for approximate nearest neighbor search. Although these algorithms are not in Spark MLlib yet, they are popular algorithms used in the machine learning community. For example, the exact KNN, UMap, and DB scan, they are part of the scikit-learn library. And the IVF flat is part of the meta-Fayes vector search library. The last group, which introduced the cross validator, is an important PySpark operator. It helps you search the best parameters for your machine learning algorithm. So it usually involves training the model multiple times. Therefore, it is very suitable for GPU acceleration as it requires intensive computation. Our ML accelerator also provides a GPU version of it optimized for GPU. I believe you are already very familiar with Spark algorithms. So the next, I'm going to showcase some algorithms that are not in Spark yet. The first one is the exact k-nearest neighbors. And the slide shows the APIs of the algorithm. Similar to the Spark convention, the application code creates an estimator object and set the algorithm parameters, such as the top K. And the next will fit a model from a data frame. This fit actually does nothing. It only memorizes the pointer to the data frame. And the computation-heavy part has two key APIs, K neighbors and exact nearest neighbors join. The K neighbors will return a distance column and nearest neighbor IDs of a query data frame. And this API is inherited from the scikit-learn library. And the next API, exact nearest neighbor join, will return all pairs of query and item vector alongside with their distances. And this API is similar to PySpark locality-sensitive hashing. The next algorithm I'm going to introduce is the UMap algorithm, which is known as Uniform Manifold Approximation and Projection for Dimension Reduction. So this algorithm can help you project any high-dimensional data into lower dimension. And in this slide shows the case of visualization. I project a high-dimensional data into 2 dimensions to understand exactly how many clusters are in your data set. And the dataset minister is a popular one used by the computer vision community. And from the projection and visualization, we can see the UMap projection, the data points from different clusters, they are more isolated from each other. And if we count the number of clusters, we know that clearly there are in total 10 clusters that match the ground truth of the minister data set, which contains the digits of handwritten digits from digit 0 to 9, exactly 10 clusters. We hope that this UMap can help Spark users to make use of this algorithm from the Spark framework. The next algorithm is the DB scan, which is for clustering. DB scan works differently from k-means that will propagate the neighbor of a point to its neighbors. And on some data sets, such as these ring-shaped data sets, the DB scan will achieve ring-shaped clustering results, while k-means does not achieve that. The DB scan is a widely extensively used algorithm from scikit-learn. And one disadvantage is that it requires intensive computation. The computation complexity is known as n squared, which n represents the number of vectors. So this is the great workload for GPU acceleration. In our experiments, we observe more than 10x speed up when using GPU acceleration. And the ML accelerator exactly provides the GPU implementation of this algorithm. Next, we also want to understand what are the benefits of GPU acceleration. To understand that, we conduct experiments comparing the case with and without GPU acceleration. We set up clusters on the AWS Databricks cloud. And for CPU cluster, we requested 2 worker nodes and 1 driver node. And for set up GPU cluster, we also request 2 worker nodes, with each worker node has 1 A10 GPU. The workload-wise, we mainly evaluate the end-to-end machine learning practice, which start from reading feature vectors from Parquet file, and then pass these vectors into a machine learning estimator to fit a model. To ensure the workload requires intensive computation, we use 1 million rows and 3,000 dimensions. Note that the data set and the benchmarking scripts are publicly available, so the results are reproducible. In our repository, we also contain the notebooks that without any programming, just click and run, and you can get an understanding of how GPU acceleration works. This slide shows the performance comparison without and with GPU acceleration on 8 different workloads, from the logistic regression, linear regression, PCA, random forest, to k-means. This runtime is shown on log scale, and it reflects to the speed up. We observe about 6x to 100x faster. And among all these workloads, the k-means shows the greatest speed up. This is mainly because k-means has the highest ratio of compute compared with the data loading and the communication cost. So it benefits the most from GPU acceleration. This slide projects the speed up into the cost benefits measured by the money paid to the renting those cloud machines. And the dark green line shows the speed up without and with GPU acceleration. And the light green one projects this speed up into the cost when renting the AWS machines to finish the computation. We observe about 3x to 58x cost benefit. So although the unit price GPU instance is more expensive than the CPU instances, but with the GPU acceleration, the whole workload can finish much earlier, and that reduces the total duration time. And same here, k-means here shows the greatest cost savings among all the workloads. And I hope these data are helpful to you to motivate enough to try the ML accelerator. And if you have any concerns, feel free to get in touch with us anytime.
Okay, so I'm going to pop back in here. These results that Jinfeng just shared, these are essentially micro benchmarks. In practice, you're probably going to have a more complicated ML application that's going to have maybe an ETL part preceding the ML training part. Maybe you're likely going to do some cross-validation. So I'd like to share some additional optimizations and contributions in one case that we've made to Apache Spark to address sort of more and optimizing more end-to-end use cases. So the first one is something that we call stage level scheduling. So Jinfeng mentioned that our library Spark Rapids ML is built on top of cuML. That's the Rapids project that I had mentioned at the beginning. And that has a constraint that the workers that are doing the training during the fit function have to run one worker per GPU. You can't double them up. And that's because they rely on this communication library called NCCL that is GPU optimized and has that constraint. And if you don't do that, you can have deadlock. So you're faced with this constraint that for that fit part, we have to have one, and we're mapping these worker tasks onto Spark tasks. So it boils down to having one Spark task per GPU for that fit stage. Now, if you had an ETL stage, you're reading the files in from Parquet, you're decoding them, or you're doing feature engineering, those can benefit from multiple tasks running per GPU. So the idea behind this stage level scheduling is to get the best of both worlds and be able to, on the fly within the same Spark job, change the allocation of tasks to GPUs. And this is accomplished through support in Spark, and a team member contributed that for GPUs specifically as the resource. And then also has support in our library, Spark RAPIDS ML, to dynamically change that task per GPU when it's doing the fit operation. The other sort of kind of end-to-end flavored optimization that we have targets the cross-validator. So in cross-validation, you're breaking up the data into multiple folds, and then each fold takes turns being an evaluation with the rest of the data training. And then for each of those folds, you're sweeping over multiple parameter choices. Our library, with our API compatibility, is designed to be compatible with all those things. So you can use it with the built-in PySpark ML tuning cross-validator, but the performance isn't going to be awesome, because what winds up happening is the training data or the evaluation data gets copied into the GPU redundantly multiple times, like for within a fold and then for each parameter sweep. So what we've done is kind of refactored that cross-validator so that the timeline snippet looks more like at the bottom, where we copy the training data once to the GPU for the fold and then iterate over multiple parameter values just for that one copy. So what we've put all these elements together in this final benchmark that we're going to show. And in this benchmark, we're doing an ETL phase using the RAPIDS accelerator for Spark SQL, along with the Spark RAPIDS ML accelerator, plus those two things that I showed you, the stage level scheduling and the optimized cross-validator. And the setting involves the Fannie Mae mortgage data set, which is a public data set made available by Fannie Mae, the single family loan performance data set. You can go and download it from their website. It's 800 gigabytes uncompressed. Our benchmark runs it out of reading it in compressed form, stored in S3. It does compress down quite a bit to like 26, 27 gigabytes. And then the ETL phase comes in, accelerated with GPUs and running multiple tasks per GPU to create a 2.6 billion record by 28 column data set that then gets fed into Spark RAPIDS ML, logistic regression for the GPU side, and the CPU counterpart in MLlib for that side of the CPU side of the benchmark. Environment is, and then cross-validator, threefold cross-validator with sweeping over 8 parameters. The environment is again Databricks, AWS. This time we're using 16 nodes instead of the 2 to be able to fit all the data in GPU memory, which is an important thing we have to get the best performance. By the way, logistic regression is doing elastic net regularization, both CPU and GPU. So these are the results, kind of broken down for the ETL phase and the ML phase, and then overall. The ETL, turns out it's not a huge part of the computation here. It's mostly the ML part. And we're seeing pretty significant benefits on the ML, kind of overall, 5 to 6x, and then cost-wise about 5x reduced cost. And then the accuracy is pretty similar for both CPU and GPU. So this is just kind of another bit of evidence of the value that GPUs can bring to the table, but sort of from more of an end-to-end perspective. Okay. So in terms of roadmap, what we're looking to do is, Jinfeng mentioned that we have some algorithms that are in Spark ML lib that we accelerate with a matching API. Then there's some algorithms that are in RAPIDS QML, no counterpart in Spark ML lib, like UMAP and DBScan. So there are a few others like that we think could be of value to deploying and running in Spark clusters. These include accelerated ARIMA, accelerated auto-ARIMA, which are really awesome to parallelize, and then other approximate nearest neighbor vector search algorithms based on more sort of graphical, nearest neighbor graph iterative approaches. Some of the algorithms aren't feature complete for MLlib, like we don't have a weights column for k-means. By request, we can work on adding support for those. Along the lines of cross-validator, pipelines is something that we're looking to accelerate as well. There, again, paying attention to minimizing data copies. We don't want to, round trip data between GPU and CPU for every stage in a pipeline. We want to be more clever. Another bottleneck is transferring data from JVM to Python workers. That's kind of happening the conventional way right now, but NVIDIA CUDA actually has support to transfer data without leaving the GPU from one process to another. That's called CUDA IPC. So we're looking to incorporate that. And then additional algorithms in Spark ML lib. We're lacking latent Dirichlet allocation. We don't have ALS. These are algorithms that are not in QML. So it's an extra effort to first implement kind of the C++ layer and then bring them into the Spark API. That link there will take you to a discussion on our GitHub. If you have any input on what we should do, how we should prioritize these, what algorithms you'd like to see, please go there and provide input. We'd love to see that and get that kind of guidance. One other thing I'd like to mention on the roadmap side is what we call out-of-core performance. So I mentioned that to get best performance with our library, ideally we want all the data that we're iterating over to fit in the memory of all the GPUs in your cluster. If that doesn't happen, some of that data spills over into the host, into the CPU, and that's not a great situation. It is supported, but performance can degrade significantly, especially for some of the algorithms that don't have as much compute to I/O. So that solution today is based on a kind of a paging mechanism similar to virtual memory in the Linux kernel. The good news is that we can look forward to Grace Hopper GPU superchips that have an integrated CPU and a GPU that are connected by a very high-speed link to become more mainstream and essentially solve this problem for us. And that's what this plot shows, that an engineer on our team created a POC leveraging that architecture as well as system-level support for it to essentially show that there's almost no performance penalty when you go out of core, which is what happens in this plot as your data set grows right between, on the x-axis, 6 or 7 million rows. It starts bleeding out. On a conventional Hopper GPU in an x86 PCIe-based system, our current solution kind of blows up, whereas this sort of more optimized solution behaves much better. So that's something else to look forward to. Some takeaways. We're an open source project, Apache v2 license, minimal code change, only import change. At this point, even that, there are ways to eliminate if that's a blocker for anybody. Pretty significant cost benefits depending on sort of computation to IO ratio of your algorithm and parameter regimes. We can run it on all Spark, hosted Spark, on-prem, etc. The trickiest part in terms of deploying this is getting the RAPIDS dependencies installed, cuDF, cuML, that stuff. Luckily, those are all available as pip packages, so you can pip install them into a custom Docker image or use init scripts. One other slide I'd like to show before getting to the last slide is about the broader GPU accelerated ML DL on Spark ecosystem. Folks may not know, but other popular ML algorithms like XGBoost, PyTorch have Spark integrations, in PySpark specifically. In fact, in those two cases, they were open sourced by Databricks not that long ago. So really appreciate that from Databricks. They actually work similarly to Spark Rapids ML, very similar architecture, and kind of inspired our architecture, actually, on the XGBoost side. They can be used with Spark clusters with GPUs. And then our team, our NVIDIA Spark team, works on sort of making sure that that touch point to the NVIDIA stack shown at the bottom works well in terms of examples, alleviating bottlenecks, things like that, and even contributing to XGBoost and other repos to sort of address those problems. We've done a lot of work with XGBoost, especially to make it play nicely with the the Rapids accelerator for Spark, SQL accelerator. Yeah, so with that, final slide with links to the Spark Rapids repo for the ETL side, our repo for the ML side of the project, and an email address. And then I showed earlier the link to our discussion where we'd love to get input on any algorithms that out there that you'd like to see GPU accelerated. So with that, we're open to questions.